In this video, we are going to be going over how to calculate isotope abundance for any atom, as well as going over several practice examples. Now let's get started. To start, it is important to know what an isotope actually is. Now, an isotope is when you take the same atom and you change the atomic mass, or you change the number of neutrons that it has. So with the 16 oxygen isotope here, you could see that the atomic mass is 16 and the number of protons is 8. Because this is close to the average atomic mass of 15.999 as seen on the periodic table, this would be the most abundant isotope here of oxygen. And now moving on to the 17 oxygen isotope, we could see that the number of protons stays the same because the atomic number of oxygen is the same, and it's the same for the 18 oxygen isotope as well. Now these will be less abundant because they both are deviating further away from that average atomic number, so their abundance is obviously going to be less. So again, to summarize, the main thing about an isotope that you need to know is that there are different atomic masses for each, which will in turn change the abundance of said isotope in the actual element of, in this case, oxygen, but this applies to all of the atoms on the periodic table. Now, in order to calculate the abundance of certain isotopes, you're going to use this formula down here, in which you can analyze the problem and determine what from it is missing. So you take the relative atomic mass from the periodic table, and you set that equal to the mass of isotope 1, so I1 is isotope 1, times the abundance of that isotope. And then you add that to the second isotope, so that's 2, and then the abundance of that isotope. And then if you have more than 2 isotopes, you keep going with that process, and as you can see down here, ensure that all abundances total to 100%. If they do not total to 100%, then you're missing an isotope, or you are trying to find that isotope abundance, so you would solve for the problem in that way. Now we're going to go over some practice examples so this can be better explained with a problem. This question is asking, use the information in the data table to find the average atomic mass of silver. Okay, so we have the isotopes here, silver 107 and 109. They give us the abundance of these in the percent here. And we're also given the atomic mass of said isotopes. So we want to find the average atomic mass of silver. Now this is probably saying that we are not given a periodic table, so we do not know this. So we have to find the average atomic mass. You set that equal to silver 107, which we can see that the atomic mass is 106.91. Multiply that by the percentage, divided by 100. And we have to add that to the second isotope, which has a higher atomic mass because it has more neutrons. Multiply that by the percentage. And that will give us our average atomic mass. Now these numbers add up equal 100%. So we're good there. So the average atomic mass is equal to, now let me grab my calculator real quick and calculate this. Okay, and we get 107.868. Now if we were to take a look at our periodic table, we can see our answer is correct for silver, in which case it is correct. So we know that we did this process right. Another example here. So iridium, which has the atomic number of 77 on the periodic table, has 2 stable isotopes. The percent abundance of these isotopes can be determined using mass spectroscopy. Which one of the following options is consistent with the mass spectrum for iridium. So we take a look in our periodic table and we find iridium has an atomic or average atomic mass of 192.22. So using these percentages on here, let's just start off with A to see if that is close or not. So we can use these percentages given here and the AMUs to see what the average atomic mass depicted in each of these graphs are. So starting with A, we have 191 times 0.627 plus 193 times 0.373. I'm going to circle A in red. Now for B, we have 191 times 0.373 plus 195 times 0.627. And finally, in blue, we have C, which was 191 times 0.373 plus 193 times 0.627. And now go ahead and do all of these calculations on your own, and we can from there determine which one is closest to that average atomic mass of 192. So as we can see, C is closest to our answer of 192.22. So we're going to end up choosing C as our correct answer here. Moving on to our second example here. Rubidium has two naturally occurring isotopes. 85 rubidium with a mass of 84.9118 AMUs and 87 rubidium with a mass of 86.9092 AMUs. If the atomic mass of rubidium is 85.47, what is the relative abundance of 85 rubidium? So let's write out what we are given here. We have 85 rubidium is equal to 84.9118 AMUs, and then the 87 rubidium is equal to 86.9092 AMU. And we are given the atomic mass, which is 85.47, and that can be found on the periodic table. And now it's asking, what is the relative abundance of 85 Rb, or rubidium? So we're going to use that formula again. So we got 85.47 is equal to, we're going to start with the 85 rubidium. So we have the 84.9118 AMUs times the percent abundance, which we do not know. And now we're going to add that to the second part. We get 86.9092 AMUs times 1 minus x, because we want to get to 100%. So 1 minus the percent abundance of the isotope of rubidium that has the mass of 85 would give us 100%. So we do this, and that is all of it written out. So now we have to solve this. Okay. So we write out 85.47 is equal to 84.9118 x plus 86.9092, and we have to subtract, we're distributing here, this, and we have to subtract 86.9092x. Okay, now we're going to want to get the numbers on one side and the variables on the other, so let me do this calculation real quick. In this first part we get negative 1.4392, and now we're going to combine the x terms. and we get negative 1.9974x. And now we divide the whole thing by negative 1.9974 to get what x is equal to. We get x is equal to 0.7205. So that means that, if we remember how we set this up, the 85 rubidium would have an abundance of 72.05%. And that means the 87 rubidium would have an abundance of 1 minus this number. Which would be about 27 or about 28%. We'll write it out like that. And we are just going to verify our answer here. So if you want, you just multiply the abundances of 85 rubidium and 87 rubidium times their AMU or their mass, and we should get the answer being 85.47. So I'm going to write this out just for practice. So just to verify our answer, we are now going to check to see if those percentages are correct by plugging into the formula we had before. So we're going to take 84.9118 AMUs times 0.7205, and then add that to the second mass of 86.9092 times that mass of times the percentage of 0.2795. And we should get 85.47 as the average atomic mass of rubidium. Now we're going to plug this into our calculator and see if we got the right answer. And we get that the answer is 85.47, which we can see is correct, so that we know these abundances here are indeed correct. And this is our last problem here. There are only two naturally occurring isotopes of copper, 63 copper and 65 copper. And copper has an atomic mass of 63.55 AMUs. And it is asking, what is the natural abundance of each isotope? So this is very similar to the last question, where we're going to have to use a variable of x. So we take 63.55 AMUs, set that equal to the 63 copper, which we know has 63 as a mass. Multiply it by the abundance, which we don't know. Then we take the 65 AMUs. Then we multiply that by the 1 minus x value there, because we don't want it to go over 100%. And now we have to distribute our variables here. So we get 63x plus 65 minus 65x. So this is a relatively straightforward question. Now let me just get my calculator here. So we get negative 1.45 is equal to negative 2x. Then we divide the whole thing by negative 2. Then we get x is going to equal 0.725. So we now know that 63 copper isotope is going to have an abundance of 72.5%, and the 65 copper isotope will have an abundance of 27.5%. And these are your two final answers here. If you want to confirm this answer, you can go up to the equation, use the average atomic mass formula, multiply these percentages by their atomic mass, and you should get the 63.55 relative atomic mass, which is also on the periodic table. I hope you found this video helpful. If you did, consider subscribing to the channel or leaving a like or a comment. Thank you.